Hi friends, welcome back on our YouTube channel. In today's lecture of classical mechanics, we will discuss about elastic collision in 2 or 3 dimension. So, here we will discuss about elastic collision in the laboratory frame of reference and also the elastic collision between two particles in 2 dimension in the center of mass frame of reference. We have already discussed about center of mass frame of reference and also elastic collision in 1 dimension between two particles. So first of all, elastic 2 or 3 dimension collision in laboratory frame of reference. So here we have a particle of mass m1 and this particle is moving along x direction with velocity u1, and here we have another particle of mass m2 and this particle is at rest in laboratory frame of reference. So this is the case before collision. Now after collision, particle having mass m1 move in this direction with velocity v1. It means it is making an angle θ1 with x-axis, and the particle of mass m2 moving in this direction with velocity v2, and this particle is making an angle θ2 with x-axis. So this is the case after collision. So after collision. Now from the law of conservation of linear momentum, since here we have elastic collision, so linear momentum as well as kinetic energy remain constant. So from the law of conservation of linear momentum, since linear momentum is a vector quantity, so the linear momentum along x direction and linear momentum along y direction will be constant separately. So we apply the law of conservation of linear momentum in x direction. Since particle of mass m1 moving with velocity u1 along x direction, so its linear momentum along x-axis will be m1 u1, and this particle is at rest, so its linear momentum will be 0. Now the linear momentum of this particle along this direction is m1 v1, and since this particle making an angle θ1, so we find the component of linear momentum along x direction, so this will be m1 v1 cos θ1, and in the same way, if we find the linear momentum along x direction of this particle, then this will be m2 v2 cos θ2. In the same way, if we apply the conservation of linear momentum along y direction, then since this body is moving with velocity u1 along x direction, so its linear momentum along y direction will be 0, and this is at rest, so its linear momentum along y direction is 0. So the total linear momentum before collision along y direction is 0, and if we find the component of linear momentum of this body along y direction, then this will be m1 v1 sin θ1. So this is m1 v1 sin θ1, and the component of linear momentum along this direction means along negative y direction of this body is m2 v2 sin θ2. Now we take the linear momentum of both body either along positive y direction or along negative y direction. So if we transfer it in positive y direction, then this will be minus m2 v2 sin θ2. So 0 is equal to m1 v1 sin θ1 minus m2 v2 sin θ2. From the law of conservation of kinetic energy, so total kinetic energy before collision and total kinetic energy after collision will be constant in elastic collision. So the total kinetic energy before collision is half m1 u1 square plus half m2 u2 square, and the total kinetic energy after collision is half m1 v1 square plus half m2 v2 square. Since u2 equal to 0, so this value will be 0, and half half and half will be cancelled out. So m1 u1 square is equal to m1 v1 square plus m2 v2 square. Now m1 u1 equal to m1 v1 cos theta 1 plus m2 v2 cos theta 2, and 0 equal to m1 v1 sin theta 1 minus m2 v2 sin theta 2. So here we have three equations and there are four unknown quantities. What are the unknown quantities? v1, v2, theta 1 and theta 2. So we have only three equations with four different unknown quantities. So their unique solution cannot be determined because at least four equations we required to get the unique solution of these four different unknown quantities. Thus, we have to determine four unknown quantities v1, v2, theta 1 and theta 2 using these three equations, which is impossible. So, one more equation is required. So, to determine one extra equation, we use a particular condition m1 equal to m2. So, if m1 equal to m2, then these factors will be cancelled out. So u1 equal to v1 cos theta 1 plus v2 cos theta 2, and from this equation this m2 will be m1. So m1 will be cancelled out. So 0 equal to v1 sin theta 1 minus v2 sin theta 2, and from here this will be m1. So m1 and m1 will be cancelled out. So u1 square equal to v1 square plus v2 square. So u1 square equal to v1 square plus v2 square. Now we square and add these two equations. So on squaring this equation we get u1 square equal to v1 square cos square theta 1 plus v2 square cos square theta 2 plus twice v1 v2 cos theta 1 cos theta 2. Now if we square this equation, so 0 is equal to v1 square sin square theta 1 plus v2 square sin square theta 2 minus twice v1 v2 sin theta 1 sin theta 2. Now if we add these two equations, then u1 square plus 0 is u1 square. We take v1 square common in these two factors. So in bracket cos square theta 1 plus sin square theta 1, which is 1. So here we have v1 square. Also we take v2 square common here. So in bracket cos square theta 2 plus sin square theta 2, which is 1. So here we have v2 square. Now we take twice v1 v2 common in these two factors. So in bracket cos theta 1 cos theta 2 minus sin theta 1 sin theta 2. So here we just write twice v1 v2 cos theta 1 cos theta 2 minus twice v1 v2 sin theta 1 sin theta 2. Now we take common twice v1 v2 here. So in bracket cos theta 1 cos theta 2 minus sin theta 1 sin theta 2, and this will be formula of cos theta 1 plus theta 2. So u1 square equal to v1 square plus v2 square plus twice v1 v2 cos theta 1 plus theta 2. Now this u1 square will be replaced with v1 square plus v2 square. So if we put here v1 square plus v2 square in place of this u1 square, then v1 square plus v2 square and v1 square plus v2 square will be cancelled out. So twice v1 v2 cos theta 1 plus theta 2 equal to 0, or cos theta 1 plus theta 2 equal to 0, and from here we get theta 1 plus theta 2 equal to 90 degree. Thus after collision the particles move in two mutually perpendicular directions. Now we have this equation, another equation is this one, third equation is this one, and fourth condition we got theta 1 plus theta 2 equal to 90 degree. So here we have four equations, and also we have four unknown quantities that are v1, v2, theta 1 and theta 2. So by using four equations, four unknown quantities can be determined easily. Thus by using these four equations, v1, v2, theta 1 and theta 2 can be determined. Now, a value of scattering angle. In the laboratory frame of reference, there are no limitation on the value of theta 1 or on the scattering angle. So a scattering angle can have all the possible values. Now, elastic 2 or 3-dimension collision in the center of mass frame of reference. From the definition of center of mass, the position vector of center of mass is given by RCM is equal to m1 u1 plus m2 u2 divided by m1 plus m2 into t. Since particle having mass m2 is constant in laboratory frame of reference, so u2 equal to 0. So RCM is equal to m1 u1 upon m1 plus m2 into t, because we consider here that the particle of mass m2 is constant or is at rest in laboratory frame of reference. So we got RCM this value. So this we got because in laboratory frame of reference u2 equal to 0. So the velocity of center of mass with respect to the laboratory frame of reference is VCM equal to dRCM upon dt, and RCM is this one. So if we differentiate this equation with respect to t, then the differential of t with respect to t is 1. So VCM is equal to m1 u1 divided by m1 plus m2. Now here we have center of mass. This is the particle of mass m1 moving with velocity u1, and this is the particle of mass m2 moving with velocity u2. This is the case before collision. Now after collision, we consider that the particle of mass m1 moving with velocity v1 dash, and it is making an angle theta with x-axis, whereas the particle of mass m2 move with velocity v2 dash, and it is making an angle theta with negative x direction. So this is the case after collision. Velocity of particle in center of mass frame of reference before collision. So velocity of particle of mass m1 in center of mass frame of reference before collision is u1 dash equal to u1 minus vcm. This vcm is the velocity of center of mass, and u1 is the velocity of particle of mass m1 in laboratory frame of reference. Since vcm is m1 u1 upon m1 plus m2, so we put this value here. Now we can take u1 common in between these two quantities. So u1 dash equal to m2 u1 upon m1 plus m2. How we get this value? Because u1 dash equal to u1, and in bracket 1 minus m1 upon m1 plus m2, and by taking m1 plus m2 LCM here, we get m2 u1 upon m1 plus m2. So u1 dash equal to m2 u1 upon m1 plus m2. Velocity of particle of mass m2 in center of mass frame of reference, u2 dash equal to u2 minus vcm, because the particle of mass m2 is at rest in laboratory frame of reference, so u2 is 0. So we just put vcm this value here. So u2 dash equal to minus m1 u1 upon m1 plus m2. So these are the values of velocity of particle of mass m1 and m2 in center of mass frame of reference before collision. Now velocity of particle in center of mass frame of reference after collision. Velocity of m1, v1 dash equal to v1 minus vcm, and velocity of m2 is v2 dash equal to v2 minus vcm, and v1 and v2 are unknown quantities which we have to determine. Since center of mass frame of reference always remain at rest in this reference frame, so total linear momentum will be 0. It means total linear momentum before collision and total linear momentum after collision will be 0. It means the momentum of the particles must always equal and opposite, because total linear momentum is 0. Therefore, momentum before collision, m1 u1 dash equal to minus m2 u2 dash, because total linear momentum is 0. So m1 u1 dash plus m2 u2 dash is 0, or m1 u1 dash equal to minus m2 u2 dash. In the same way, momentum after collision is m1 v1 dash equal to minus m2 v2 dash, because also here we have m1 v1 dash plus m2 v2 dash equal to 0. So we get this relation. Since in elastic collision total kinetic energy remains conserved, so half m1 u1 dash square plus half m2 u2 dash square equal to half m1 v1 dash square plus half m2 v2 dash square. Now half will be cancelled out. Also m1 u1 dash equal to minus m2 u2 dash. So u2 dash equal to minus m1 upon m2 into u1 dash, and m1 v1 dash equal to minus m2 v2 dash. So v2 dash equal to minus m1 upon m2 into v1 dash. So we replace this u2 dash with minus m1 upon m2 into u1 dash, and this v2 dash by minus m1 upon m2 into v1 dash. So m1 u1 dash square plus m2 into minus m1 u1 dash upon m2 whole square is equal to m1 v1 dash square plus m2 into minus m1 v1 dash upon m2 whole square. Now from here m2 and 1 m2 will be cancelled out. So here we have m1 u1 dash square plus m1 square u1 dash square divided by m2, and here m1 v1 dash square plus m1 square v1 dash square upon m2. Now u1 dash square is common here and v1 dash square is common here. So if we take u1 dash square common here, then in bracket m1 plus m1 square upon m2, and in right hand side v1 dash square is common, and in bracket m1 plus m1 square upon m2. Now m1 plus m1 square upon m2 will be cancelled out. So u1 dash square equal to v1 dash square. So u1 dash square equal to v1 dash square, and from here u1 dash equal to plus minus v1 dash. So we take square root on either side and we get u1 dash equal to plus minus v1 dash. Similarly, we can get u2 dash equal to plus minus v2 dash. So we just replace here u1 dash and v1 dash by using these two equations in terms of u2 dash and v2 dash. So we get this relation. Thus, in center of mass frame of reference, the magnitudes of the velocities of the particles do not change, but their direction changes. Because u1 dash equal to v1 dash and u2 dash equal to v2 dash, it means the magnitude of the velocities of particles do not change in center of mass frame of reference. And also here we have plus minus sign, so their direction may changes. Now value of scattering angle. In center of mass frame of reference, particle of mass m1 is moving in this direction and it is making an angle θ1, and velocity after collision is v1 dash. So the component of v1 dash in x direction, that is v1 x dash, is equal to v1 dash cos theta, and the component of v1 dash in y direction is v1 y dash, and this is equal to v1 dash sin theta. In laboratory frame of reference, the particle of mass m1 moving in this direction and it is making an angle θ1 with x-axis, and its velocity after collision is v1. So its x component, that is v1x, and y component is v1y, and v1x equal to v1x dash plus vcm. If we compare these two frame of reference, and v1y equal to v1y dash, so there is no change in the velocity component along y direction, whereas the velocity component in x direction changes. So this is the comparison of deflection in C frame and in laboratory frame. Now from this diagram, tan theta 1 equal to V1y upon V1x, and V1y equal to V1y dash, and V1x is V1x dash plus VCM. So tan theta 1 equal to V1y dash upon V1x dash plus VCM. Now V1y dash is V1 dash sin theta, V1x dash is V1 dash cos theta. So tan theta 1 equal to V1 dash sin theta divided by V1 dash cos theta plus VCM. Also, the velocity of center of mass VCM equal to m1 u1 upon m1 plus m2. Now we multiply and divide right hand side by m2. So m1 upon m2 equal to m2 u1 upon m1 plus m2, and m2 u1 upon m1 plus m2 is u1 dash. So we replace this value by u1 dash. So VCM equal to m1 upon m2 into u1 dash. Also u1 dash equal to plus minus v1 dash. So we replace this u1 dash with v1 dash. So VCM equal to m1 upon m2 into v1 dash. Now we substitute the value of VCM here. So tan theta 1 is this one, VCM is this one. Now we replace this VCM by m1 upon m2 into v1 dash. So we get this relation. Now v1 dash is common in denominator and it will be cancelled with numerator. So tan theta 1 equal to sin theta upon cos theta plus m1 upon m2. So tan theta 1 equal to sin theta upon cos theta plus m1 upon m2. Now a special case is if m1 is greater than m2. So if m1 is greater than m2, so cos theta plus m1 upon m2 will be definitely positive. Now if this value is greater than 0 or positive, then tan theta 1 will be definitely less than infinitive. It means theta 1 is less than pi by 2. Next case, if m1 equal to m2. So if m1 equal to m2, then this will be 1. So cos theta plus m1 upon m2 is 0 when cos theta is minus 1. Because m1 upon m2 is 1, so cos theta plus m1 upon m2 equal to 0 if cos theta equal to minus 1. So if this is 0, then tan theta 1 equal to infinitive, and in this case theta 1 equal to pi by 2. So theta 1 equal to pi by 2. If m1 is less than m2, then tan theta 1 can be either positive or negative, and therefore all values of theta 1 can be possible in this case. So here we end our session. In today's session we have discussed about elastic 2 or 3 dimension collision in laboratory frame of reference as well as in center of mass frame of reference. So goodbye.